Okay, so this is one of the classic physics problems. This is a problem on projectile motion. And the idea with projectile motion is that you can really start by writing down the kinematic equations in both the x and the y direction. Really, before you do anything else, you can write down these kinematic equations. So I have the kinematic equations in the x direction, where I've put x for position, vx for velocity, and ax for the acceleration, and in the y direction. So I have the y for position, vy for velocity, and ay for acceleration. Okay, so in this particular problem, what do I know? Well, what I know is that I have some initial velocity as a vector, which is 65 meters per second, and it is in the direction of 35 degrees above the horizontal. This is hard to do math with this information though, right? So instead, what we're going to do is we're going to say that the initial velocity as a vector is some component in the x direction, I hat, plus some component in the y direction, so that's j hat, which means I need to pick axes. So I'm going to pick my axes such that the 0 is where the ball leaves the top of the cliff, x is in the horizontal direction, and positive y is in the upward vertical direction. So I can take my vector here, this v0, this green arrow, and I can separate that vector into components. When I do that, that means the magnitude of the vector, which is just v0, I have a vx, which is v0 cosine theta, and a vy, which is v0 sine theta. So I'm going to write that down. So I have a v0 cosine theta and a v0 sine theta. In other words, I have 65 meters per second times cosine of 35 and 65 meters per second times sine of 35. What else do I know? Well, what else I know is that this happens on Earth, so I know that the acceleration due to gravity is, with the axes I've chosen, 0 in the I direction. Gravity only acts downward. And it has a component of minus g because it's downward in the y direction, and I chose up to be positive. So if I look at my kinematic equations, then every place I have an ax, that just goes to 0. Every place. And every place I have an ay, I'll just put a minus g in there. Every place I have a negative, or an ay, minus g, and here, minus g. Okay, so what does that give me? Well, what that gives me then is that I can start to learn some things about these equations, right? So for example, this first equation, or rather the second equation here, tells me that Vy is equal to, or sorry, Vx, I don't know where that came from. Vx is equal to Vx naught. In other words, at every time t, at all time t, the x direction doesn't really change. And in the y direction here, we said that we can rewrite this same equation, but we don't know time. So let's, instead of the equation with time, let's pick the one that doesn't have time. And we can rewrite that equation as Vy squared is equal to Vy naught squared plus 2 times negative g times y minus y naught. So Vx is equal to 65 cosine 35, and Vy is equal to the square root of 65 sine of 35 degrees squared plus 2 times minus g, and the final was negative 115 minus 0. And that we simplified a little bit. So we'll do the square root of 65 sine of 35 squared minus 2 times g times 115. Now, the question we decided to ask about this problem is, what is its final velocity right before it hits the ground? Find v just before landing. And that means that we want the final velocity, which is just the square root of vx squared plus vy squared. That's not a kinematic equation. That's just the Pythagorean theorem. And so when we plug in what we have for vx and vy, you get a number. I'll let you plug all that in, and that's the end of the solution for this problem. Notice that we could have asked a lot of other things. We could have asked about time and height and range and all those different things, but the method is the same. We start by writing the kinematic equations, apply what we know about vectors, apply what we know about the acceleration due to gravity, and then we're done. Okay.